move on to Morgan's talk. So Morgan is, so to speak, the black sheep of this mini symposium, since he's the only one who's not talking about Hawkes processes. Morgan finished his PhD last autumn in University of Sao Paulo under the supervision of Antonio Galvez, and he's now a postdoc at Unicamp University. And he's going to talk about a metastable model. Morgan, we don't hear you.
Hello.
Yeah, that's great.
Okay, so how do I?
You can share screen.
I don't have the little thing on the bottom to share screen. Maybe we should put me as.
Morgan, you are co-host, so
you can.
You are allowed to share your screen.
I don't see the things that I should use to share screen. Yeah, okay. Can you see?
Great.
Okay, so thank you everybody to be here. So I'm going to speak about result of metastability in a stochastic system of spiking neurons, which is not with Hawkes process as Christophe just said. So it's basically a model that has been developed by my PhD advisor and also Eva Lasherbara. And this will be a specific instantiation that was proposed in a paper from 2018, I guess. So, okay, so overview of the things I'm going to talk about. So first, I would like to talk about metastability in general a little bit, so that everybody is on the same page. And then I will try to speak about the more specific framework about metastability that I'm going to work with. Then I will define the model. And I will try to present one of the results that I've been working on during my PhD thesis. And while I hope I will have some time to enter into the details, but I'm not sure. And at the end, I want just to talk a little bit very quickly about the other results and the other possibility and similar models that you can consider. Okay, so metastability. If you take the definition from Wikipedia, metastability is the property of a state seemingly stable, but such that a tiny perturbation can push it toward an even more stable state. So I guess this is a pretty good definition. Actually, I'm not. Metastability is a term that is used, but I don't like it very much. So I'm not going to use it because everybody uses it. But so there was an expression used by physicist Bernard Derrida, which was dynamical phase transition, which is not really used anymore. But I think that it tells pretty well what it is. So phase transition, I guess everybody knows what phase transition is. You have some system and you just change the parameter of the system. At some point, there is a qualitative change in the behavior of the system. So metastability is basically a phase transition, but which happens dynamically. So you don't have a phase transition because you change the parameter, but at some point in time, because the system encounters some perturbation, for example, because it's dynamic, it undergoes a change in behavior, qualitative change. So example of metastable phenomenon. So metastability is discussed in a lot of different fields. So for example, you have metastability in physics. So avalanche typically metastable phenomenon because you have some amount of snow on the mountain and just stay there in a seemingly stable state. And at some point you have some little perturbation. So for example, you have an earthquake or something, and the slow to fall down in, so this is another more stable state in nuclear physics. So typically radioactivity is a metastable phenomenon, supercooling waters. In electronics also, you can talk about metastable bits. So of course in mathematics, typically in the field of mathematics that model phenomenon in physics, in economics, and even in philosophy, some authors such as Sartre or Simondon have used the concept of metastability. But why do we care about metastability in neuroscience? So it has been, I guess, in the last 20 or 30 years, it has been increasingly discussed, but by a lot of neuroscientists. But it's not very clear if everybody is always talking about the same thing. So typically, people are saying that the brain is metastable in the sense that it uses metastability to change from a network to another periodically in order to be able to process the noisy information of the environment we are in. But I've been trying to read some of these neuroscientific papers about metastability. It's not very clear if every of these papers are talking about the same thing. And it is rarely talked about in a mathematically rigorous perspective, in my opinion. So this is what I've been trying to do. And so here I give some reference of the neuroscientific literature about metastability. And also, yeah, so just to give so this is some, I will be very quick about it because this is some work I've been doing with Christophe. So this will be an example of metastability in the brain. So this is a recent work I've been doing with Christophe, and it's almost done. So typically working memory. So there was some this is what you are seeing are experimental data of working memories that were done in the 80s, where basically you have a monkey facing some experimental setting, and some cue is presented to the monkey, and then the cue disappears for some times, and at the end of some delay duration, the monkey has to give some answer accordingly to the cue and to get its reward. And what you see are the intracerebral registration of the spikes in the monkey, in the cortex. And what you see is something that is kind of, in my opinion, typical of metastability, where you have some stimulations that push the system towards some activity, and then even if the cue disappears, the activity kind of stay in these metastable states for some times, and at the end it resolves, either because the monkey gives a right answer, or maybe because it can stop before the answer because the monkey is distracted. And yeah, so this could be, for example, one phenomenon that could be explained by metastability in the brain. So, but the framework I'm going to use for metastability is something that comes from statistical mechanics. So there was a paper in '84 by Cassandra et al., in which they introduced the following characterization for metastable dynamic in statistical mechanics. So there is basically 2 points. The first point is that you have some absorbing state. So it's not necessarily an absorbing state, because there is some metastable dynamic where actually you have some state and you go from a state to another periodically. So this is not absorbing, but in the approach I'm gonna use, the state will always be an absorbing state. And what happens is that the time it takes to reach this absorbing state is memoryless, that is exponentially distributed. So this is the first point of the 2 points characterizing metastability. And the second point is that before reaching this point of this absorbing state, the system basically behave like it was stable. So actually, this is not very obvious how to characterize in a rigorously mathematic way what does it mean, but in some cases you can. And I hope I will have some time at the end to explain a little bit in more depth what the second point means, but my talk will be mostly concerned with the first point. Okay, and in this paper, so from Cassandro et al., they do this for, in the field of interacting particle systems, they do this for the contact process and the Curie-Vest model. Okay, so what is the model first? So I will first present the model in a very generic way, and then you'll see that we're gonna consider the more simpler instantiation of the model, which is, I guess, the simplest I've been considering, because I guess it is the best in a short talk like this to present. But let's see just the general way first. So you have some set representing the neurons, so countable set. For each neuron I in this set, you have a set of presynaptic neurons. So basically all the neurons that give synaptic input to this neuron I. For each neuron I, you have a membrane potential. So it takes value in the positive integers, non-negative integers, just for because it is simpler in this modeling setting. And then you have two things. You have the spiking times and the leak times. And these are modeled with spawn processes. So, well, the spiking times, this is this process Ni star. And while there is nothing to say about it, I mean, there is nothing specific about modeling a spiking activity with point processes because it is quite natural, but maybe it's a little bit different for the leak time. So the leaks is basically when we have neurons. We know that very often you have, when the neurons is not affected by anything, you have this natural continuous decrease of the membrane potential. So here we choose to model this by some point process. So typically at all the atoms of this point process, the membrane potential of the neuron is immediately abruptly reset to 0. So this is simplification, but this has a nice consequence that in the end what we get is in interacting particle system, and so we can use all the literature and all the results that we have in this field, and it makes the system more tractable. And the last thing is some spiking rate function phi. So it basically take as an input the membrane potential, and it gives you the spiking rate, so the rate of the point process n star at any time t. Okay. So then the dynamic of the process is as follows. So actually the leak process, so n dagger is a Poisson process of some rate gamma simply. So gamma is a parameter of the model, is the leak rate. And the point process n star is not a Poisson process, and it's a process that has a fluctuating rate, which, as I just said, is given at any time t by phi I of xi I t. And all the dynamic of the process actually is given by this line here. So basically what this means is that you have this LIT, which is the time of the last event affecting neuron I. So when I say the last event, what I mean is either a leak or a spike. And you integrate all the spike of the presynaptic neurons up to this time t. So what this means is, if you have a leak because you integrate on nothing, then the moment potential of the neuron is reset to 0. The same happens if you have a spike, but the other thing that happens when you have a spike is that all the postsynaptic neurons have a membrane potential which is increased by 1 unit. Okay, So now the simplification that we do. So for phi, you could choose various functions. It could be something like a sigmoid function or rectify linear unit. But the choice that we have made is to take simply a step function. So basically the only thing that we care about then is whether the moment potential for a given neuron is equal to 0, in which case we say that the neuron is quiescent, or whether it is strictly positive, in which case we say that it is active. And so what you get is an interacting particle system so this is a continuous time Markov process taking value in the state space of any sequence of 0 and 1 indexed by the neurons. And okay, and so once you have this system, so you have the degree of freedom, basically, which is the activation function. As other thing that you have to choose is the graph of interaction of the network. So how the neurons are connected to each other. And here, what I will be presenting is one of the simplest setting when you have the following. So basically, integers are indexed on the integers, so positive and negative. And the structure of the interaction is nearest neighbors. So each neuron has only one neighbor on the left and on the right. And so this defines a process of infinitely many neurons. And you also define a finite version of this process, which is just the same thing, but instead of taking infinitely many neurons, you just take a finite window of the integers from -n to n. And of course, so it's the same, it's nearest neighbors, but of course you have some condition at the border. So if you are neuron n, then you have only one neighbor on n-1 for your presynaptic neurons. And it is the same for -n. Okay, so just a picture, because a picture is always simpler than some formula. So what happens is that you have this. For example, if some neuron is in state 1, so active at time t, it spikes at rate 1. And then when it spikes, what happens is that the neuron becomes inactive, so state 0, and the neuron on the left and on the right becomes active. And the other thing that happens is this leakage, so it happens at rate gamma. And if the neuron is active, it becomes quiescent, and nothing specific happens for the neuron on the left and on the right. Okay, so these are just some simulations. So this is simulation for I value of gamma. So what you see are the extinction time histogram and extinction time survival function. So remember, the thing that we are interested in seeing is whether or not the extinction time, because here, yes, I didn't say, but so obviously because of standard reason related to irreducibility of Markov chain on finite state space, there is one absorbing state, which is a state where everybody dies. Every neuron is quiescent, and once you've reached this state, so because it's absorbing, you don't get out, and you always go to this state almost surely. And so what we are looking at is the extinction time, and you can see here for gamma I, it is not exponential, because the red curve here is the density of an exponential function, and here the red curve is the survival function of an exponential. And you can see that neither the histogram or the survival function are anything close to an exponential law. And also here you have some trajectory, typical trajectory of the system. So you can, these are the number of active neurons in the system. And you can see that what happens is that it simply continuously decreases towards 0 with some spikes, but not much, and nothing really interesting is happening. But something different happens if you take gamma low. So if you take gamma low, small value of gamma. You can see that both the histogram and the survival function are very close to the system is close. The extinction time is close to an exponential law, as you can see from the histogram and the survival function. And the typical trajectory, something different happened now. So you can see here you start with 100 neurons, and what happened is that it simply decreases very fast until reaching some kind of stable values, and then it oscillates more or less around this value for some long time, because you can see that here the time unit was 3, here it's few hundreds, few thousands, and then because of some statistical deviation, it reached the absorbing state and stays there. So you can see it is kind of reminiscent of the kind of picture I showed you a few slides ago about working memory. Okay, so, but the work I've been doing during my PhD was not doing simulation. The objective was to prove results. So now I will present one of the results that I've been proving. So you define the time of extinction. So I just gave the formal definition of the time of extinction. So nothing specific, it's just the time at which every neuron in the system is quiescent or in state 0. And so the result that you prove is the following. So there exists some critical value for the system, such that if you take gamma less than this critical value, then the time of extinction renormalized converge weakly to some exponential distribution, or in distribution it converges to an exponential law. Okay, so I would like to speak a little bit about how you prove this kind of result quickly. So the main thing that you prove is this first line here, for this line. So you prove that the limit of this thing here goes to 0. So you can see the memorylessness appearing here. And so of course here, you would like to have the expectation of 2n, because normally this is the object with which you normalize the time of extinction. But for some technical reasons that I will not have time to explain, you introduce some time scale beta n that is defined like this. So the unique value such that this is equal to exponential minus 1. And then you prove that this thing goes to 0. And then the result follows that. So this implies by kind of standard arguments that this thing here converges to an exponential in law. And then you prove that the expectancy of tau n and beta n are equivalent. And so this proves the result that you want to prove. But really the main point here is proving this. So the two lines after are mainly standard arguments. And the main ingredient of the proof is here. This is proving this limit here. So how you do this is you find some smart bond, and then you prove that this bond here goes to 0. So you can see that here, for example, I put, so when I put a superscript, I just mean that the states, initial state is the superscript. So here the initial state is A. And if I don't put any superscript, what I mean is that the initial state is a state where everybody is active. So you get this bond here, and you have this set is here F. So it can be any set. This is true for any set. And then what you want to do is to find some set. So you can see that there is a part where everything is in F, and a part which is kind of out of F. And you want to find the right F such that these things can go to 0 if you choose wisely the way your n goes to infinity. And so the way you get this F is you use some of the properties of the system that you can prove. So what are these properties? So these are the properties of the infinite system. So remember, there is a finite system and an infinite system. And you can prove that the system converge weakly to the infinite system. When you start from everybody active, it converge. So of course, the system has an invariant measure which is trivial, which is the state where everybody is dead, like in the finite process. But you can also prove that it has a non-trivial measure, invariant measure mu, and that it converges toward it when you start with everybody active weakly. And then this object, this invariant measure mu, is one of the central objects that you use to prove the thing that you want to prove. So, in particular, you can prove that if you define its density, so the number of the probability that a given number is a given neuron is in state 1, it is strictly positive if you take gamma small enough. So this is phase transition. And you can also show that it is spatially ergodic. So you have this result here. If you take the sum, it converges to rho, right? But if you take the empirical mean, and so this is the thing that you want to show that it goes to 0. And what you do is that for this f that we wanted to find, you take fb, where fb is defined like this. And what you can see appearing here is this kind of empirical mean here. So you can see why we are going to use spatial ergodicity. And so I don't have time to enter into the details, but what you do is this first part, you use phase transition and something called duality. And for the second part, you use basically the spatial ergodicity. And this work because you have chosen this set here. Okay, so now I would like to speak a little bit about other results and similar models that you can consider and results that you can obtain with these models. So we've proven that for gamma small, you have this convergence of the time of extinction towards the exponential, but you can also prove that if you take gamma big enough, you don't have this convergence. So indeed, the value of gamma is determining the metastability of the system. And actually, what you have is that if you take the convergence is to 1. So what this means is that basically, asymptotically, the time of extinction is deterministic. So of course, you can also consider other graphs for the interaction. So one of the graphs that I have been considering is the complete graph. So, and you can prove the same kind of result. So the proofs are a little bit different because you cannot use this limiting measure mu, but while you can find some way to prove the same result, actually the result is stronger because you can prove that it holds for any gamma positive and not only for gamma small. And as I said at the beginning of the talk, another thing that you can that we have done is this work with Christophe Pouza, where we have considered a system that is a little bit more complex, where you have a feature of synaptic plasticity. And so in this model, you also have this complete interaction. And we have shown numerically the same kind of behavior, the same kind of result of metastability. Okay, and so to finish, I would like to speak a little bit about the second point. So during this talk, I've been talking only about the first point of metastability, which was this convergence of the time of extinction toward the memoryless distribution. Now I would like to speak a little bit about the second point, which is how you characterize the quasi-stationarity of the system before extinction.
Morgan, if we want to be able to take questions, you should go very
fast. Okay. So do I have 1 minute?
Yeah, 1.
Okay. So okay. I don't want to explain things too quick. So thank you for your attention.